Okay, ladies and gentlemen, as we've just talked about Riemann sums and area, I'd like to take a look at area from a different perspective now. Let's get a little sketch. Let's have a function. Let's call it function f. Now let's not make it f of x because I'm going to use x for something else here. Let's put a value down here. Let's say that we're going to go from a and we're going to go from b. And let's let x be some value on the interval a comma b. So x is going to be somewhere in here. Let's pretend it's right there. Therefore, using a little bit of knowledge, the area under this curve, okay, the area under here will be given as a of x. Because it's dependent on how far we go here, it's definitely in terms of x. So we're going to make that a of x. That's just the function of the area. Now if I think a little bit about this function, let's say I didn't want to stop at x. Let's say I moved a little bit farther down the road and I went to x plus h. Well, this point up here, we could call it p, and this would be x comma f of x. Now that's a value, right? It's a value between a and b. So really, this function can't be in terms of x. I can't use x twice as the general case for the value and for a numerical value and for f of x. So, well, let's hold on to that for a minute. I'll do another video on that in a second. I don't think I have to get into that right now. This will be q. This will be x plus h, f of x plus h. Okay. This distance here would be h. And what we've got is a trapezoid here. And that trapezoid looks like this. And it comes down, maybe I could call this PQ, and I could call this S, and I could call this R. And you can see that I've got a nice little trapezoid here, PQRS. And that little trapezoid is going to have an area, and that area we'll call the change in area. So as I move a little bit farther down, it's the change in area as I move from x to x plus h. Now, let's do a little bit of a thought idea here. I'm going to do two different ideas and then link them together. So the first concept is, let's look at this area function. So area function. Now, if I was to take the area function, take the derivative, if I was, by definition, that would mean the limit as h approaches 0 of delta a over h. So the change in a over h. Okay, it's kind of interesting. Now, this change in a, delta a, would be given by the area up to x plus h minus the area up to a. So delta a will equal this entire area subtract that area. So these two ideas can be put together, and what you would have is the limit as h approaches 0 of a x plus h minus a of x over top of h. And that would be the derivative of that area function, just by definition. Okay? So this is just a thought by definition. Now, let's have another thought here. Let's look at this trapezoid. Now, the area of a trapezoid is going to be 1/2. Now, I'm going to look at this trapezoid this way. I'm going to fold it down. So this side length will simply be how high it comes up to hit this, and this is going to be f of x plus h. And this side length is simply going to be f of x. If I have another color, I'll use it. I've got blue, I guess. So this length here is f of x plus h from there to there. And this length is f of x from there to there. This is simply h. So that means that the area of this trapezoid will be 1/2 h f of x plus h plus f of x. That's the area of the trapezoid. Now, the area of the trapezoid is equal to delta A. That's what the area of the trapezoid is. So delta A is equal to 1/2 h f of x plus h plus f of x. Which means that if I take this, I'm going to be able to plug it into here. And it's also equal to this. So there's no, all of this is equal to each other. A of x plus h minus a of x. So all of these are equal to each other. This one, and delta A, and this one. So what I'm going to do is I'm going to take this value, and I'm going to go back to our idea that the derivative of our area function is the limit as h approaches 0, only this time I'm going to write in f of x plus h plus f of x over top of h. So I've got the h's will cancel because it's the limit as h approaches 0, so they actually don't equal 0 yet. I'm going to allow the limit to take hold. As the limit takes hold, this h value goes to 0. And what I end up with is 1/2 f of x plus f of x, which is f of x, which is very interesting. Very, very, very interesting indeed. Because what that means is that the area function for the area under the curve f of x is the antiderivative of the curve itself. So the area function, the derivative of the area function is equal to the curve itself, which means that the area function is the antiderivative of the curve. Which means if I'm given a curve f of x, and if I want the area function underneath it, what I do is I take the antiderivative of the function. That's pretty cool. We'll be back in a minute to expand.